So here we will solve this problem with the help of sympy in Jupyter Notebook. You can also use Thorny, but here we will use Jupyter Notebook. So because the mathematical symbols are very nicely presented in Jupyter Notebook. So this problem, as you know, a thin semicircular ring pinned at A and B, and it is loaded at its crown, and you have to find out the reactions at these two pins. And the structure is symmetric because the geometry is symmetric and the loading is symmetric. So this is X and this has to also be X. If this is H, this has to be H. So twice X is P. So, and if you cut here and draw the free body diagram and calculate the bending moment if you find out the bending moment expression here, just take moment about this point, and this M clockwise is H. For H this is the moment term, and for X this is the moment term. So this is the moment expression because X is P by 2. So we replace X by P by 2. Now let us work it out using sympy. So here this is the Jupyter Notebook, and we are launching the Jupyter Notebook. Yes, it is launched, and a new file Python 3. So from sympy import start and press shift and enter together. So the next line is generated, and here just give this init printing for better printing. So now symbols. So what are the symbols? P, H, R, theta, and let's see P, H, R, theta, and EI. So E and I equal to symbols within quote the same thing. That means we are declaring P, H, R, theta, E and I as symbolic variables. So we are putting them inside the sorry. So let's correct it. Yeah. Paste. Okay. This. Yes. Now it's okay. So we are declaring P, H, R, theta, E and I as symbols. Then what is the expression for M? M is a variable, and the expression for M is half into P into R into 1 minus cos theta minus H into R into sine theta. M, you can just see what you are getting. Yes, you are getting this. So let's check. So M is theta minus HR sine theta. Okay. Now U is equal to 1 by twice E into I integrate this m square into r, and the variable of integration is theta, and theta varies from 0 to pi by 2. So this is u. So you can check the value of u by just printing it and pressing shift enter together. So this is what you are getting as u. So let us check. So this u should be, u is, as you know, twice 0 to pi by 2. Okay, we are u equal to twice 1 by twice ei 0 to pi by 2 m square r d theta. So the limit is from 0 to pi by 2. So limit is from here to here, because the bending moment expression changes here. So we are not integrating from 0 to pi. Rather, we know, since this is a symmetric structure, the strain energy stored in this half is same as the strain energy stored in this half. So we are finding out the strain energy stored in this half, and we are multiplying it by 2, and that's what we are getting. Now we have to find out del u, del h, and we have to equate it to 0. So how to find out del u, del h? So let us du, dh. So this is just a variable name. You can use any variable name. So diff means differentiate u with respect to h, and then you get this. So if you want to see what is du dh, so this is du dh. Now you have to equate it to 0. So you are equating del u del h to 0, and you are finding out h. So what would be the equivalent statement? Yes, so solve, that means you are solving an equation where you are writing just du dh, that means du dh equal to 0. Whatever is written here, that would be equated to 0 and taken as an equation, and you are finding out h. So solve. So h is this. So the value of h is given. H is 0.3183 pi. So in this way you can solve this problem. So you can also use Thorny for this, but here see the mathematical expressions are nicely shown. So here for this problem we will use sympy. So as you know, a cantilever wooden beam is supported by a steel guy wire. So this is a cantilevered wooden beam, and this is a guy wire steel. So the cantilever wooden beam is subjected to, so if you cut the wire here and expose the tension, then the cantilever beam is supported by a transverse load which is p minus s sine theta, or p minus s by 2, and the axial load is s cos theta, and here it is s square L by twice AE is the axial strain energy for the guy wire. Only the L is this L by cos 30. So we have to carefully write the expressions for strain energy. So we start Jupyter notebook as we do, then from sympy import star, then init v printing for nice looking printing, then not init v printing, it is init printing, yes. So now the symbols are, one is P, one is S, one is for the wooden beam A underscore 8, this is the area, this is the wooden beam elastic modulus, then this is the wooden beam I, for the steel beam only AS and ES, the subscript S for steel, subscript W for wooden. Anything else? L, yeah, L equal to symbols, the same things, only enclosed by quotes. So here this copy, so we put here, paste, and we'll put quotes. Shift enter. And for the bar, the bending strain energy for the wooden beam, the bending strain energy is, so U, let's call it UW. UW1 is bending part, and that is P minus S by 2, because sine 30 is half. P minus S by 2 is the force, and delta is P minus S by 2 L cube by 3 EI. So that is half P minus S by 2 into P minus S by 2, S is capital, into L cube by 3 E, this is wooden, 3E, this is wooden, item. So the bending part is over. Now what about the axial part? The axial load is S cos 30. So P square L by twice EI, twice AE. So S into cos 30 means pi by 6 P, this is P, so this is square into L by A W into E W. Done. Leaves unders. I think the beam part is okay. Oh my god, so many errors here. Forgot one multiplication sign here. Now it's okay. So U, so let's see what it is giving for U W. So it's given this for U W. So looks okay. So only S cos pi by 6. Let's check what is the axial force. S cos 30, S cos pi by 6, P square, S cos 30 square, L by A W E W. So fine. Now what about U steel? There is a guy wire. Guy wire is, so S one thing, S cos theta square PL by twice AE. So here missed out the 2. Yeah. So shift enter and shift enter. Yeah. Now looks better. Now US is S square. This is the force square into L. In place of L, we have L by cos pi by 6. S square L by twice A E into AS into ES, and that gives your US. So let us write US. This is US. S square L, in place of L, L by cos 30, P square L by twice AE. So total strain energy is UW plus US. This is the total strain energy. Now du ds equal to diff u with respect to s. That gives you the equation. So this ds has to be solved. So the solution is, or you just can solve like this, solve equal to solve du ds, sorry, du ds, and we are solving for s. So solve, so this is solve. Looks quite complicated. Now we just substitute the values. Sol dot subs, it is substitute within second bracket, the dictionary. So L, what is L? L is 150, so far as I remember, L is 150. The cross sectional area for wood is again 150. The cross sectional area for steel is 0.333, and E for wooden beam is equal to wooden beam, not equal to will not work, we have to give colon, then E for wooden beam is 14, E 4, 14 into 10 to the power 4, and E S is equal to, for steel, 2.1, E 6 kgf per cm square. And what else is required? Let's see what happens. So equal to again, So equal to will not work, so we have to give colon. So this is the dictionary. So invalid syntax. So sol dot subs. Here this is not this bracket 1, this bracket, and within that the dictionary. So yeah, okay. Sol is a list, so sol 0, yes. So let us write it as sol 0 so value equal to this. Now we print value. Yes, so IW is not given. IW would be 1/12 10 into 15 cube. I12 is IW is I underscore W is 1 divided by 12 into 10 into 15 cube, I suppose. Yes, I think now it's okay. Hopefully, and this is what we are getting, 1.4768p. So this is our problem and this is the answer. So 1.476. So the answer is S equal to 1.48p, and we are getting quite close, 1.4768p. So this is all. Thanks.